it's time for some combinatorics clock problems. So the first one we're looking at is from the 2023 AIME 1, and it's the 14th problem, which means it's hard. So hopefully you've already read the problem, so I'm not going to go over it. So the first thing we're going to do is we're going to ignore the clock flavor text, because that's bad. So we're going to instead think about the two hands on this clock as just the two numbers that the hands are pointing to. And instead of calling it 12, we're just going to call 12 0. And we're going to take all numbers mod 12. So we start out at 0, 0. And then if we move let's say the minute hand or whatever, if we move that one, we'll increase the left number. And if we increase the hour hand by 1, if we move the hour hand clockwise, we'll increase the right number by 1. So we could have a sequence of numbers like this. And like I said, we take numbers mod 12. So if we were ever at say 11, 5, and then we move the minute hand clockwise, we increase the left number by 1. Instead of going to 12, 5, we'll go to 0, 5. And so what we need to ensure is that in 144 moves that we make, we'll never go back to the same move. So we go through all 144 distinct ordered pairs like x, y, where x and y are integers mod 12. So so let's solve the problem now. And it's a very Olympiad-like problem. So we're going to consider a smaller number because the reasoning that we're going to use is going to generalize to 12. So let's think about maybe 6 instead of 12. So we have to go through 36 positions. That's the number of positions I went through with your mom. Okay, so you have to go through 36 positions, and the 0th position we'll say is 0, 0. And then the 36th position is also going to be 0, 0. We're not going to write that for now. So let's just, to get a feel for this hand moving thing, with the analogy of increasing a number by 1 each time, let's just write out some examples. So our 0th position is 0, 0, and then let's say our first position we move the minute hand clockwise, so that's 1, 0. And then the next move we move it again, 2, 0. And our third move, I don't know, maybe we increase the hour hand now by 1. And let's just say we keep doing this. What was I trying to do there? 4. Let's say we increase the minute hand again. 5. Let's say we increase the hour hand. And our 6th position, let's say we increase the minute hand. Okay. So far we haven't repeated any position yet, which is good. For example, we could have actually messed up already if we just moved the minute hand every single time. We could have gone 0, 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, up until we got to 5, 0. And then in our 6th position, we go back 0, 0. We've already repeated a position. That's bad. But so far, this example seems to be working. So what we claim is that after we've made our first 6 moves like this, there either exists exactly one sequence that will go through all 36 positions after this, or there exists no positions. So there exists at most one position. We basically predetermined the rest of the moves we're going to make. So let's see why that is. Okay, for example, let's consider now, notice here we're at 2, 1. Okay, this is our third position. So let's consider at some point we're going to have to go to the position 3, 0. Right, in our 36 positions, 3, 0 is one of them. So at some point we're going to have to go there. And the question is, from what position before are we going to get there from? Well, it has to be either 2, 0 or 3, 5, because 5 plus 1 is 0 mod 6. But it can't be 2, 0 because we already had that here, because we used that to get to 2, 1. So it has to be 3, 5. And we're going to increase the right number by 1. Notice that we also increased the right number by 1 here. And in fact, let's just go back and let's just draw a red arrow for which number we increased at each turn, because this is going to be pretty important. That's beautiful. Okay. Oh, that arrow is trash. Okay. Beautiful arrow. Beautiful arrow. Okay. So we must have gone from 3, 5 to 3, 0. And just like how we went from 2, 0 to 2, 1 here, and we increased the right number, we also increased the right number here. So now let's consider 4, 5. We could have either gone there from 3, 5 or 4, 4. And wow, isn't that wild? We already had to use 3, 5 to get to 3, 0 here. So therefore we can't go from 3, 5 to 4, 5. So it must be 4, 4 that we come to 4, 5 from. And once again, it's that right number that we have to increase by 1. And notice I'm picking here. I'm picking the numbers whose sum here is 3 mod 6. Like 2 plus 1 is 3 mod 6, 3 plus 0 is 3 mod 6, 4 plus 5 is mod 6. And we can use similar reasoning to continue on like this. Like 5, 4. Only way we can get there is from, let's use the red one, is from 5, 3 before. Okay. So we've like predetermined now that if we ever get to 5, 3, which we will, the next number has to be 5, 4 for sure. Okay. And now this reasoning will generalize to like any number. And what is basically happening is that the move we make, whether we pick the left number to increase by 1 or the right number to increase by 1, it's solely now determined based on the position on like the sum of these two numbers taken mod 6. So for example here, notice if the sum of our two numbers is congruent to 2 mod 6, now because this one time we made the decision to increase the hour hand by 1, the right number by 1, every time now from here on, we're also going to have to increase the right number by 1. So this position of like left, left, right, it's going to repeat 6 times until we get back to 0, 0. Now, the conditions we've described here are necessary, but not sufficient to describe which sequences work for the problem. So let me explain that. So we've determined that in order for our sequence of moves to get back to 0, 0 in 36 moves, this is going to have to hold true. Like our pattern, the pattern we pick in the first 6 moves for which number we pick to increase, it's going to repeat 6 times. But actually in this case, if we repeat this pattern, well then consider once we get to position 12. In position 12, once again, it's going to repeat. So we went from 0, 0 to 4, 2 the first time. So if we scale up again, we're going to be at 8, 4. But 8 is just congruent to 2 mod 6. So we're going to be at 2, 4 at position 12. And position 18, we go up. The left number increases by 4 and the right number increases by 2. So now we're at 6, 6, but that's 0, 0. Oh no, something has gone terribly wrong because we weren't supposed to return back to 0, 0 until we were at position 36. So what caused us to prematurely return to 0, 0 is the fact that 3 times 2, 4 is equals to 0, 0 mod 6. And this can't happen. What's going wrong here is that 2 is not relatively prime to 6, and nor is 4. Shoot, where's the mouse? Neither is 4. For example, if we picked 1, 5, 3 times 1, 5, that equals 3, 15, which is 3, 3. And that's okay. That's okay. This is bad. Another example is 3, 3. If we pick that, then notice after 2 times 3, 3, so that would be position 12. We'd already be at 0, 0 again too. So the condition is that at position 6, our two numbers must be co-prime to 6. And it turns out that this condition is necessary and sufficient, which is we just pick our first 6 moves and then make sure that at position 6, our two numbers are co-prime to like 6. And then from there on, we're guaranteed that if we repeat these moves over and over again, we'll end up back at 0, 0 with no repeats. So the proof of this is left as an exercise to the reader. And this is an AIME problem anyway, so we're not obligated to prove anything. But now let's just go back to the 12 case. Because we changed 12 to 6 to make it easier to give an example. But now let's just go back to 12 and compute. So we need to find the number of ways such that in position 12, our ordered pair is either 1, 11. It can't be 2, 10 because 2 and 10 are not co-prime to 12. It can't be 3, 9 either. The next one is 5, 7. So our 12th position has to be 1, 11, 5, 7, 7, 5, or 11, 1. Those are our only choices. So the number of ways to pick a left or right for such that our 12th position is equal to 1, 11. That's just 12 choose 1 because we have 1 left and 11 rights to pick. For 5, 7, that's going to be 12 choose 5 because we have to arrange 5 lefts and 7 rights. And like this. So on. So if we compute these, I believe 12 choose 1 is equal to 12. 12 choose 5 is equal to 792. And these just repeat like that. So summing all these up, if we do some quick maths, that should give us 1608. So therefore n is equal to 608. Okay. I'll be very impressed if you somehow understood this. This is incoherent nonsense. Okay. So now let's move on to the second clock problem. Here it is. The OMMC problem 25, and this is from this year's OMMC. So if you don't know, the OMMC is a student-run competition. So this is a student-written problem by Square Man. That's his AOPS username, and it's a very good problem. This problem is the best problem ever. It's also really hard. So definitely give this problem a try if you haven't seen it before, because maybe that'll help you appreciate how slick the intended solution to this problem is. So watch as I struggle to draw a clock here. Okay, so just hopefully you've read the problem, whatever. So, okay, so this problem feels like it should be easy, but if you try it seems like there's no nice pattern going on, and there's going to be a lot of irregularities that happen. Some edge cases you have to deal with if you try to manually count this. But it turns out, in fact, this problem, we can have a general formula for the answer to this problem for any number of hands and for any speed of the hands that makes sense. Okay. And so here's the really slick solution to this problem. What we're going to do is at the start, there's going to be 3 hands, right? I've placed them slightly apart so we can differentiate between the 3 hands. I should color them actually. So let's color 1. That'll be the hour hand, the minute hand, and the second hand. So our fly A, starts out on the second hand. And now we'll define 2 more flies. This is the really slick part, and you'll see why in a moment. So we're gonna place a second fly B, on the minute hand, and then fly C on the hour hand. And so these flies B and C will obey the same rule as fly A, which is after this, if fly B, okay, it's if fly B is on the hand and it crosses another hand, fly B and will switch onto the other hand. And there will be a fly on the other hand too. So if we have, I don't know, at some point maybe we have I'll color code the hands again. So let's say we have the minute hand is chilling here, and then the second hand is catching up. And fly C is on this hand, and fly A is on this one. As the second hand rapidly catches up to this minute hand, once it's crossed, then fly A will now have switched to the. Fly A will now have switched to the. What do you call it? We'll have switched to the second hand, and fly C will have switched to the minute hand. As this one continues to spin faster. The second hand continues to spin faster. So this is how we're gonna define this procedure. And so the question is, why are we doing this? How will this help us count how many revolutions the fly A has taken? So here's the clever part. Notice that when these two hands cross, fly A remains ahead of fly C. So the order of these flies is preserved. Once the three hands set off, the order is permanently that A is ahead of B is ahead of C, which is to say that A will never like cross around to go be between C and B. A will always be at the front. So fly A will never cross fly C will never cross fly B. It's like a train, A, B, and C going around in a circle. And that's exactly what it is. We'll treat it like that. It's a train. And so notice that after at midnight, how many if we take how many revolutions the three flies have taken in total, that's just going to be how many revolutions the minute hand made plus how many revolutions the second hand made plus how many revolutions the hour hand made. Because every time a hand makes a revolution, that counts as like one. I'm high right now. That counts as one revolution for one fly. So in 12 hours, the second hand makes 720 revolutions. The hour hand makes 12 revolutions, and the minute hand makes 60 revolutions. Wait, that's not even right. What am I saying? How many revolutions? Oh, wait, the minute hand makes 12 revolutions. Wait, what am I? Yeah, minute hand makes 12 revolutions, and the hour hand makes 1 revolution. So in total, the flies A, B, and C make 733 revolutions in total. Okay, and now just notice that since A never crosses to C, fly A cannot have made more than 1 revolution than fly B or fly C. But it can't have made less revolutions than B or C either, because it is clearly ahead of the others in this train. So that's terrible reasoning, but hopefully you're convinced that now we just divide by 3, and we take the ceiling of that to get our final answer of 240. I'm struggling to do basic math. This is sad. 245, and that's our final answer. Okay. I'm pretty sure this solution made even less sense than the first one, but hopefully you enjoyed this video and hopefully you actually watched it. So yeah, okay, bye.